Hello all, and welcome back to the Aimless Electron. In this episode I'm going to introduce a new series that I'm just basically calling the dummy power load. This is going to be, as I just stated, a dummy power load. It originally started off as the idea of making a desktop power supply, and that's kind of like the de facto rite of passage for any hobbyist electronics to make your own desktop power supply. I thought it'd be a good idea maybe to make the dummy load first, and I know that there's going to be a lot of technologies and ideas that I can transfer from that over to the power supply eventually, and then I can use that to test the power supply. Not to mention all the things I'm going to be able to learn in the process. So stick around and we'll go through that. Also, let me know, I've got a new mic, some of you might be able to see that. If it sounds better, which I'm hoping it does, leave me a comment about it, and I'll see you soon. Alright, now let's talk over our design goals real quick. First, this is going to have constant current, as pretty much any dummy load would, and also it's going to have constant voltage. Speaking of voltage, I want this to be able to go up to 30 volts max at 8 amps max. That means I want a max of 240 watts of power dissipation, which I know is a lot, but as long as we have the right heat sinks, we should be fine. I want to be able to step through that 30 volts in 10 millivolt increments and the 8 amps in 2.5 milliamp increments. And I'll explain how I got to those numbers later, but it has to do with this next part. I want to use an X-Mega, I'll just write that down real quick, an X-Mega 128 to control this thing. And it has its own built-in analog to digital converters and digital to analog converters, and it's part of the reason I got at these numbers. I'll explain all that in a little bit. The next thing I actually want to talk about is a phased rollout. Very quickly, I'd like to go over the phase development that I want to do on this. The first design of this I want to be just completely computer controlled, no user interface really on the device itself. It just has the ports for the wires coming in and maybe a power switch on it. Then I want to bump it up and put some basic displays, some basic number displays on it, and maybe a few buttons to turn it on and off or maybe set some things. And finally, I want to go with a full color display, think like Rigol, and some rotary encoders on it to set things. So we'll go through these eventually, and I'll record all the steps on that, but in other parts. Let's talk about how I arrived at the steps that we had for the design. First, the DAC and the ADC are both 12-bit, and that means we have a total of 496 steps. Well, my voltage reference is going to be 2.048. Well, if we divide that voltage reference by 496 steps, we get a total of 0.5 millivolts per step. That's right, not 0.5 volts, but 0.5 millivolts per step. Just keep that in mind. There's a couple gotchas with this DAC and ADC on the X-Mega. First, the DAC. The DAC's pretty easy, except it doesn't get linear until it goes above about 150 millivolts. So the DAC has to be greater than 150 millivolts before we really consider it useful. Next, though, is the ADC. The ADC does not go rail to rail. It doesn't go all the way to 0, and it doesn't go all the way to 2.048, or your reference voltage. It goes to what it claims about 0.05 times the VREF to VREF minus 0.05 times VREF. Well, in reality, I'd say it's actually a little closer to 0.07. And I know it's not a huge deal, but just for completeness sake. What this means is you start at about 150 millivolts and go to about 2.048 minus 150 millivolts, or about 1.9 volts. At 1.9 volts, that means our range is significantly reduced. If you count this out in steps, that means we start at about 300 steps and end at about 3,800 steps. So our max range is only 3,500 steps, or about 1.75 volts. And you got to keep that in mind in case you want to go all the way up or all the way down. And that does affect the design a little bit, which I'll show in a little while. So next, with that in mind, I'll write that down that we have 35 steps. 3,500 steps. And we have 30 volts that we want to step through. Well, a nice round number to divide 30 by is 3,000, which gives us the 10 millivolts. And 3,000 fits nicely in our range. There's not much we could do with that number where it would give us nice even steps where we can hit most points. In other words, we can easily hit nice round numbers. So what about the 8 amps? Well, it turns out that 3,200 steps is a nice round number that still fits in our 3,500 range, and that gives us 2.5 millivolts per step. Works out pretty well. So when we look at these numbers as it has to do with the circuitry, we'll see how it influences what we build up with some op amps and some of the math that we have to do with these numbers. And we'll do that next. Now I'd like to talk to you a little bit about the theory behind the circuit itself. This is just the constant current side, and I'll go through that real quick. Starting off, we have our MOSFET, just an N-channel MOSFET, that will actually control the current going through the circuit and through this current sensing resistor. This is a 0.1 ohm, hopefully you can see that, current sensing resistor. A little bit on the math for that. We want to go up to 8 amps, right? Well, if you put 8 amps over a 0.1 ohm resistor, you get 800 millivolts, or 0.8 volts. I'll just write 800 millivolts. That means if we go all the way down to 2.5 milliamps, we'll get 0.25 millivolts out. If you remember, our DAC and our ADC both work in 0.5 millivolt steps. So that means we actually have to multiply it by 2. We have to multiply whatever we are sensing off this current sensing resistor by 2. And that's what the rest of this circuit really does. And it also sets in a 200 millivolt offset, so we can be in the linear region for both the DAC and the ADC. So let's go over how that works real quick, and the rest of the circuit, of course. We have this right here, that's just a current limiting resistor coming out of this feedback network that's created with basically one op amp. And if you take a look at some of the other videos on the net about building dummy power loads, you'll notice, like, Peter Oakes does a great job on this one. You want to have this capacitor in here, and it will stop the oscillations, or help stop the oscillations, but it'll be very small, like maybe 0.1 microfarad, or even smaller than that. The smaller you have this, the better response time you'll get. The next thing we have, and we'll go down here, is the actual multiplying op amp. We just have a resistor divider right here. So as long as these two resistors are very close, if not exactly the same value, we should get perfect multiplication through this, minus maybe some slight drift or offset in the op amp. Nowadays, op amps are pretty good, and when you test it, they come out pretty close to perfectly linear. And you really don't have to worry about it too much in this circuit. After it comes out of this op amp, it goes through this summing circuit. This right here is a summing circuit. And the reason we have that is we want to add this multiplied voltage to a roughly 200 millivolt offset. The 200 millivolt offset is coming from this right here. It's a bit over-engineered, I'm sure, but this ensures that nothing we do influences our reference voltage, and that nothing at our reference voltage influences our circuit. In other words, we can't feed energy either way. All this is doing is taking whatever the reference voltage is through a resistive network here and dividing it down to 200 millivolts. So whatever those resistor values happen to be, it's just based off our VREF. Ideally, this VREF is going to come from the precision 2.048 volt reference, because that's very stable and very quiet noise-wise. So it's going to be roughly 9 to 1, 10 to 1, something like that. that's pretty much it for how we're getting the signal out. Once it comes out of this op amp, it's going to be fed back into yet another op amp right here. This op amp is just basically there to take the differential between the signal coming out of our DAC and the signal going in from our AD to our ADC. That means up here is our microcontroller. And that microcontroller, again, is the XMega 128. After it comes out of this, because we're going again in 0.5 millivolt steps, we go through yet another resistor divider to bump that down to basically 0.25 or 2.5, no, sorry, 0.25 millivolt steps. That should match what's coming into the differential right here. So that's pretty much it. The important things to remember about this is you want these resistors to be matched as closely as possible. All the resistors in these pairs, well, not that pair, these pairs, these pairs, these pairs, and these pairs, for the pairs themselves, you want the resistors matched as close as possible. And there's plenty of options out there. They're inexpensive. Right now, I just match some up using my multimeters. And I'll eventually replace those with probably some single chip arrays because they'll be thermally coupled. So that means if they do drift for thermal reasons, they should pretty much drift at the same rate so it won't change their ratio. That's about it. Let's go take a look at some of the circuits live now.
Ignore this for now. This is part of the power supply, and we'll take a closer look at that real quick at the end, and I'll explain what's going on here. For the parts, we have our offset voltage buffers right here, and then in this dual op-amp package we have our multiplier for our input and then our summer for our offset voltage and the result from our multiplier. And finally we're using this potentiometer as a replacement for our MOSFET and current sensing resistor, so we don't have to have any of that built up. So basically this part right here is this part right here is this op-amp package, and this part is replaced by this, which is right here. So what we have in our meters is the input voltage coming directly from this. Then we have our final reference voltage coming from this. And I'm just going to use this one as something to point out random voltages. For instance, this should be running off of 3.3 volts, and you'll see here that we're relatively close. 3.28 is pretty close to that, right? Also, you'll notice that I don't actually have the precision voltage reference in here because something happened to my power supply earlier today and took that out, so I haven't replaced it yet. I was only using it in this demo circuit to provide the offset voltage, which it really doesn't matter. I just switched up resistors to this 15K and this 1K, and so I have the 3.28 in this case coming into the first side of this op amp, which is the first buffer, then the resistor divider into the second op amp, which is just the second buffer. From there, it goes out into our voltage summer. And our voltage summer then takes the input from this multiplier, which is on the other side of this op-amp package. And that is being fed from, again, the potentiometer. Once these kind of sum the voltage together, they are multiplied by 2, because basically this works by adding the two voltages together, which basically divides them in half because it takes the difference between the two voltages. So that's what you're actually multiplying there, is the difference between the two voltages, and that happens to sum it up. So you can see here we're getting about 2.06, 2.07 volts from our supply, our reference, and then once it's summed, you can see we're getting a little bit of drop through all this, which is fine, but we're getting basically that offset voltage plus this times 2. So this should always be offset voltage plus this times 2. Now I'll go through it a little bit. It's going to take me a little bit because this is pretty touchy to find a stable voltage that is easy to add. So let this count real quick. As you can see here, we are pretty close. We'll start off with as close as I can get it to 9 milliamps here, which is not easy. Maybe 10. Maybe if I'm closer to 10, I'll just stick with 10. But as you can see, we've got just under the actual starting value, or 2 times the actual starting value of this. If I go up again, we should see that it's pretty linear. Let's go up quite a bit to say in the 60 millivolt range here. Maybe we can get it exactly on 60. That would be helpful. And if I can get it exactly on 60 or pretty close, you'll see that we now have 320 millivolts on this side. So about 200.5 was what we started with when this was all the way down. And now we're at almost exactly double that. So I'd say we're pretty good there. We'll bump it up a little further and check out some higher. Let's try something higher like 150 millivolts if I can get on it. And as you can see, we're already getting very close, and there it is. One more will go all the way up to 250. That'll be close to the top range of this potentiometer circuit as the input, but it gives a pretty good example of how this all works. And it remains pretty linear. I'm very happy with that. These op-amps seem to be very good. So we're very close. 250 times 2 would be 500, plus 200 millivolts would be almost 699. It'd be closer to 700. But we have some error now that we've switched over from reading all the way down to the hundreds of millivolts to, or tenths of millivolts to millivolts only. As you can see, this decimal point moved over one because of the maximum range of this. Finally, let's take a look at what's going on with the power supply. I'll scoot this over just a little bit so you can see better. This is really just a standard 5-volt input. I've got some power coming in, 5-volt regulator, and then the rest of the circuit actually creates a virtual ground. This op-amp is used to create a virtual ground, and this gives it basically more current potential. It gives it the ability to supply more current. So the current that it's supplying comes out this red wire and is split up and is used as the ground plane for this circuit. And this circuit board, this breadboard, was actually made or intended to be used for more than just these 2 op-amps in this demo. That's why this is all there. For now, this is the only op-amp actually using that. The reason is, even though these op-amps are rail-to-rail, they can't quite go down to 0. So if I want something close to 0, like for instance, inputting 0.5 millivolts from this to this, I'm going to need a rail that's lower than ground, lower than this ground point. So technically, this ground point over here on this board is sitting at about 1.7 volts lower than this ground. And that's because we've got 5 volts in, 3.3 volts coming out, which happens to be what some of the logic circuits I need needs. That's why this op-amp is sitting on a different negative, because this bottom pin, pin 4, is the ground pin or the VSS pin. So this op-amp has 5 volts potential going over it, but its ground level is sitting at 3, is sitting lower than this ground level. And that's the reason for that whole circuit. Unfortunately, something happened with the power coming in earlier that took out a bunch of this stuff. That was fun to deal with right before shooting.
Okay, so that was the first introduction to this dummy power load. Let me know if you have any questions, because I know that was a lot of material to go over. This will be a multi-part series, so look for the next part if you're interested. If you've got any kind of feedback for me, if you want to give me some suggestions on how to make the circuit better or ask me why I did something so stupid, please feel free. Anyways, thanks again for watching, and if you liked it, give it a thumbs up and subscribe to the channel. But I'll see you in the next one.